look for an alternative. That's the main reason. Now, this part actually, I believe it has been covered, so we'll be going quick. Okay, it is just as a refresher for you to move to the next part. So we just should remember that for PMSM, our phase voltage equation, per phase voltage equation, is a time varying equation, AC quantities. In fact, the inductance here, this is also position varying. Okay, they vary with rotor position. It's not actually a constant when we look at the voltage, this time domain voltage equation. As we know, especially for salient pole machine, inductance is different at different rotor position, and if we plot them, so you will get a diagram like this. Okay, in self and mutual inductance varying in the rotor positions. Okay, so it's actually not a constant. In salient pole machine, you can get a maximum value and a minimum value by measurement, so which we call LDLQ, roughly. But if we look at as a self and mutual inductance, they are varying with position, right? So this equation, if we just want to use this equation to design control or to understand the transient response, is very difficult, right? One voltage current sinusoidally varying with time, inductance varying with position, so it just becomes very complicated to, if we want to look at how what's happening during transient, because in transient your speed is also changing with time, right? Then that's what leads us to the dynamic model. Okay, we want to develop a technique which can help us to analyze the performance during the transient, and that is what is dynamic model. The other equations is steady state model actually. Okay, the one that we use with our equivalent circuit, the classical equations with the pagers. Now, how do we find this equation, this dynamic model? It's actually based on our DC motor concept. Okay, so DC motor, if we remember that his DC motor has your armature voltage equation. In DC motor was that the first armature equation gives us the armature current, and okay, torque is proportional to armature current, as most of you know for DC motor. So we get armature circuit gives us the torque, and the field circuit gives us the flux, right? So they are decoupled from each other, and controlling flux and torque independently is easy in DC motor. On top of that, these quantities, the current quantities and voltage is DC, right? So that also make easy for control design. Okay, but if we want to analyze the response, transient response of a DC motor, we still have to consider this DI/dt and DIF/dt, and our torque equation is also actually have a differential term, right? Acceleration, time varying quantity. So it's also a differential equation. So if we want to handle this type of equation and use them to analyze response, the best way is to use Laplace's transformation, if you remember, right? We can convert this equation to Laplace's and can get a block diagram like this and use this block diagram to analyze response for different, for a step change of voltage or step change of torque, etc., right? But we can't do this in this phase voltage equation of AC machine. We can't use this one. We can't apply, if we apply Laplaces here, we have the trouble in inductance, because your inductance is also going to change with position. So direct use of this equation is not easy. On top of that, our flux and torque are coupled to each other. Okay, torque from the motor is actually function of current and flux, and they are coupled to each other. Okay, stator, and this flux is the resultant flux, which includes the PM flux as well as current flux. Okay, flux linkage, I mean. So that's why again they are coupled. So separation is not as easy as it was in the DC motor. So if we can get a torque equation as well, which we can see how the torque and flux are decoupled from each other, that will also be useful. So that leads us to actually our dynamic DQ model dynamic equations, okay, or DQ dynamic model of PMSM. And this our phase equation, voltage equation, our phase voltage equation, we can, when we apply transformation, we can get VD and VQ voltage like these ones. And if you compare them now with your DC, separately excited DC motors equation, you see the similarity here, right? They are pretty much same. And torque equation, for when we use the DQ model, our torque equation also becomes function of current, IQ current actually, okay? And the flux becomes function of, or rather flux linkage becomes function of ID current. So we can also get separate or decoupled torque and flux, okay, when we use DQ dynamic model. Okay, so that's the main reason why the reference frame theory, transformation, and DQ model is the key for achieving advanced control such as field oriented or direct torque control. Okay, and then I guess you have understood the reference frame theory, the transformation. It comes from the concept of rotating magnetic field actually. Okay, we can get the same rotating magnetic field that we get with balanced three-phase current also with two-phase, right? This is same rotating field can be achieved if we have two-phase. That means if we have two windings 90 degrees to each other and pass equivalent current of I, IB, IC, we should get the same rotating magnetic field. So based on that, actually the reference frame theory or transformation has come from. Okay, so this two-phase could be a fictitious two-phase. We can imagine, okay, we have two windings, one in the D-axis and other one is Q-axis, and if we pass ID current and IQ current to these two windings, it will produce the same rotating magnetic field or same space vector. Remember we discussed space vector, which combines VA, VB, BC together to give you that rotating resultant voltage, right? Or resultant flux, or the resultant magnetic field, rotating magnetic field. Okay, so now these two windings, D and Q winding, it's actually up to us how we define it. If we say that, okay, these D and Q windings are fixed to the stator, not rotating but stationary, we get stationary reference frame. If we say, okay, no, this DQ winding is attached to the rotor and rotating with synchronous speed, we will get synchronous reference frame. Okay, Or if we say, okay, this DQ are attached to arbitrarily and rotating with arbitrary speed, we will get an arbitrary reference frame. And we can easily transform from one frame to other frame, and it's all mathematical. Okay, it is all mathematical transformation only. So it is just as a matrix equation, as you have already, I believe, discussed. This matrix equation, in the stationary frame, we simply assume that this theta is 0, because theta is equal to the defined as a integration of speed, time integration of the speed, and this omega speed is the rotational speed of your frame. Okay, and in stationary case, omega is 0 because it's not rotating, so this theta becomes 0, and then we get our stationary reference frame matrix, which becomes just integer, just the numbers, right? Cos 0 will give you 1, cos minus 2 pi 3 cos 120 degree will give you half, and so on, right? We'll start getting numbers here. This is 0, this will be root 3 over 2, and so on. So you will get a matrix in stationary reference frame, which are simply the element of the basic matrix is simply numbers, and you don't need theta. That's why in stationary reference frame, right? You can get this matrix as numbers. And if we do synchronous reference frame, then this theta comes from your electrical synchronous speed. So omega is simply 2 pi f. Okay, omega is simply 2 pi f, or theta is your rotor position, but electrical rotor position. Okay, we have to remember this is the electrical rotor position. Encoder gives you theta m, so we multiply it by pole pairs to get theta electrical, which we use in this matrix to do our transformation. And so if we apply the transformation to each quantity, each sinusoidal quantity in the our per phase equation, there's quite a lot of maths you have to do. It's a matrix multiplication. Okay, you have to do a lot of maths, but at the end, when all is done, this equation transforms to the dq equation, voltage dq equation that we have seen in the previous slide. And so our if we write it in terms of matrix, here is your dq model. Okay, two equations in matrix form. And another good thing is that in these equations, in fact, the inductance, which was varying with rotor position, when we apply the transformation to the inductance matrix, we get LD and LQ, and this LD and LQ becomes rotor position independent. They become constant. Okay, so that's also the advantage. Now our voltage equations, this LD and LQ are constant. They are not varying with position anymore. Okay, so we have now a set of equations, PD and PQ. The voltage and currents are DC if it is in synchronous reference frame. Inductance is now position independent. So it becomes very much like that DC machine equation now. Okay, we can consider this like our armature voltage of DC machine, and VD we can consider it like the VF, the field voltage of the DC machine. Okay, and using these two equations, we can also use even Laplace's transformation if we wish to analyze them. Its responses, just like DC motor. Okay, or we can use these two equations to develop models. Like in Simulink, some of you may have got exposure to the Simulink PMSM model, right? So if you open that model, go under it, in fact, they have these equations only. So they only does calculation using this equation, the torque calculation or the response calculations, okay? And we can even also develop equivalent circuit of these two equations now. One thing we should note that this is our q-axis voltage. We have a term which is in d-axis, okay? Similarly, this is your d-axis voltage, but we have a term here which is in q-axis. So there is a coupling between d and q-axis in these equations, okay? But when we do, however, these two, if we look at them as an equivalent circuit, we can represent them as simply as additional voltage source in your equivalent circuit, okay? Resistance, inductance, and the equivalent voltage source. Okay, so this is omega time flux linkage is always a voltage, right? From Faraday's law, as we know. So this can be represented as a voltage in the equivalent circuit. Now that's our voltage equation. Now we also want to see how is our torque and power in dq axis, right? So if we want to analyze the motor in transient condition, we must look at instantaneous power, not the average power, okay? So for three-phase, instantaneous power, as you all know, is summation of instantaneous voltage and current of each phase and summed up together, right? VAIA plus VBIB plus VCIC. So to this equation, we can also write in a matrix form this voltage, this power equation. And then if we apply transformation to the voltage as well as to the current, dq transformation, synchronous reference frame, we will get a power, total power to the machine in terms of VD and VQ voltage, okay? And if we now substitute the VQ and VD in terms of the inductances and the resistances as we have previously, if we substitute them in this power equation, we get three distinct terms, okay? The first term here relates to the resistive loss, right? IR time I squared. So it's the resistive loss. Second term is distinctly related only to the inductances, right? LD and LQ. So this power is actually your reactive power in the machine. Okay, this is the reactive power. Third term is actually the real power. Okay, and this real power is converted to mechanical torque. Okay, so to calculate torque, actually we only need this term, the last term. Okay, only that part of the power converts to torque. So we use, so this third term we can call developed power, mechanically developed power. And taking this, if we divide this power by the speed, we will get our torque. So torque is lambda d IQ minus lambda q ID, whole thing there is a factor 3/2 and pole pairs coming from the speed. This omega cancels out because we have a omega e here. So this omega e will be cancelled out when we calculate torque. And 3/2 factor is coming because of the transformation. Okay, this 3/2 factor comes from the transformation. And if we replace our flux linkages, so flux linkage, q-axis flux linkage is simply q-axis inductance time IQ current, and d-axis flux linkage is d-axis inductance time ID current. Sorry, this is ID. plus the PM flux linkage. Okay, so if we replace these flux linkages in our torque equation here, we get our familiar torque equation for PMSM in terms of inductances and current. Okay, and the first part is related to magnet only, so we call it magnet torque, and second part is due to the difference in saliency in the D and Q axis, represented by the LD and LQ difference. So that's the reluctance torque, difference in reluctance, right? And so that is the torque equation. Okay, for us to look further. For IPMSM, LD is not equal to LQ, so this second term is important and we must consider it. Whereas in the surface type SPM machine, since LD is equal to LQ, this term disappears. We have then the torque simply as 3/2 pole pairs lambda PM IQ, and this is very similar to a DC machine torque. This first part is a constant, right? 3/2 pole pair lambda PM, all are constant. So we can even think of it like a KT IQ, like DC motor, right? And this by changing IQ, we can change torque. That means, right? And if we consider it as a IPMSM, even then it could be think the same way, 3/2 pole pairs. The flux term is lambda PM minus plus LD minus LQ ID whole thing multiplied by IQ. So this part is like a flux. Okay, this like a flux, but in IPM machine this flux may not be a constant, because we can, by changing ID current, we can vary this flux. Okay, so this equation we can think of as a constant, a variable flux time IQ, okay, or active flux. Sometimes the term in the bracket is called active flux because that flux can vary, and that's why we can get flux weakening in the IPMSM, because we can vary this flux by varying ID current. Okay, so that's the very basic. We have gone through a bit quicker because you have been through this theory already. Now let's look at the field-oriented control more. We have seen this figure already yesterday, so we'll start from there. Now you should be you should understand what we are trying to do here a bit better, right? We want to run the motor at a certain speed. So to run the motor at certain speed, I need certain torque, right? And to get this torque, as we have found that torque can be thought of proportional to IQ current. So this torque reference gives us a reference current, IQ current, okay? And we want to control this IQ current, right? And we can do that through a PI controller. So this could be a PI controller, okay? And output of that PI controller will be VQ voltage, okay? So when we are designing VQ voltage, we are actually ignoring the coupling with the D axis of Q axis, okay? And we are assuming it's as if the VQ voltage is function of only IQ current, okay? Same thing we do for the ID current control. So what are we doing with that coupling term? Okay. Usually, so you design your PI controller from the voltage equation considering simply this. Okay, you design your PI controller considering only this. Okay, the coupling term we ignore while designing PI controller. Okay, and these two term is added later, the output of the PI controller. So this is the PI controllers, Q axis and D axis PI controllers, and output is a voltage. Okay, so let's call it a VQ 0 or something. Okay, or VD 0 star, let's say. And then we add our decoupling terms to them, add them, this one and this one, and at the end we get the total VD and PQ, which you would then do an inverse transformation, okay, DQ inverse transformation to get VA, VB, VC, and this is your reference voltage for PWM. Okay, these three voltages is your reference voltage for, if you are using SPWM, they are your reference voltages. If you are using SVM, then also they are your reference voltages. Okay, so the design of this 2 PI controller is the heart of the FOC actually. Okay, speed controller is all, if you have a speed controller, then also you can design the speed controller very much like you will design a speed controller for DC motor. Okay, but more important or difference in the current controller design if we compare it with a DC motor. Okay, and so while designing, we have to consider a few things, right? We want to have, we may want to operate it with a maximum torque per ampere. We may want to operate with under flux weakening. So this ID current and IQ current reference can vary, or we may have to limit them according to the our motor's ratings. Okay, we just cannot have infinite ID or infinite IQ, right? Or we just cannot randomly select an ID or IQ value. They all depends on your operating conditions. So the limits for the current comes from your rated current of the motor, right? You cannot operate your motor above your rated current. So always, whatever ID and IQ you select, the square summation of those two current must always be less than equal to your peak rated current of the motor. So if we look at this as an equation, it's actually an equation of a circle, right, in the DQ plan. So if I plot ID for an IQ of various values in the ID-IQ plan, we will get a circle. Okay, and this circle is called current limit circle. Okay, so ID versus IQ plan, and I vary ID current from 0 to ISM and IQ or vary IQ from 0 to peak current or rated current, and ID I can calculate from this relation, and if I plot them, I will get a circle. Similarly, the voltage also, you cannot have a voltage higher than your rated voltage, right? Your motor voltage must be limited by the rated voltage. So the voltage equation is also like square sum of the VD and VQ must be less than equal to peak rated voltage of your motor. Now this VD and VQ, if we replace them with our equations, VD equation and VQ equations, we will get the equations in terms of inductances. And let's just for time being ignore the resistance drop, RD and RQ. If I ignore them, I will get a much more simplified equation for the voltage. And if you look at here, this is actually equation of ellipse, right? So if I plot the voltage, this voltage equation for various ID, IQ current, and keeping for a particular speed, I will get an ellipse like this. Okay, so this ellipse is called voltage limit ellipse. Now, if you note in this ellipse equation, we have the speed term, right? As the speed increases, this term is going to reduce, right? This term is going to reduce. So reduction of this term in an ellipse equation, what does it mean is that your long axis is shrinking. Okay, your long axis of your ellipse is shrinking, and that's why for different speed we get different ellipses. Okay, the shrinking of ellipse means that you are limited, you have limited voltage as the speed start to increase, because your voltage is fixed, right, by your battery or by your source. But with speed, this term is always keep increasing. Omega time lambda PM is always going to increase. Okay, so you are your limit is, that's why also shrinking, so which is represented by the shrinking ellipses. And the center of this ellipse, from the same equation we can show that center of this ellipse is actually the characteristic current that we define. Okay, characteristic current and zero. Its characteristic current is in the ID axis. So if we define it as a coordinate, is x-axis term is the characteristic current and zero, this coordinate of the center. Okay. So based on what is the value of characteristic current, my ellipse can move either this direction or that direction. Okay, and that also has some implication. Now before we move to that, let's also look at for IPMSM. So we have current limit, we have voltage limit ellipses. And if we want to now run it in the maximum torque per ampere MTPA control, in case of SPM, MTPA control is simply ID equal to 0. Okay, for SPM. But for IPM this is not the case. For IPM, we will need to find a particular value of ID. Okay, ID is not 0 for IPMSM. So what is this ID value for MTPA? How do we calculate it? And that actually comes from the torque equation. Okay, here is your torque equation. So current I, if we remember, we discussed this a lot last time. So current vector could be here. Okay, this is your current vector, this is your Q axis as well as your back EMF. Okay, and the angle between current and back EMF is, as we defined previously, as the gamma angle, right? Current angle. So this gamma angle is not 0 in IPMSM. Okay, in SPM, gamma angle is 0, so I and E are in phase. That's why we don't have a ID component. But in IPM, we will have an ID, negative ID current. Okay, because gamma is not 0. But we need to know what is the optimum gamma that can give us maximum torque with minimum current. That's what is MTPA, right? So to find this, you will use the torque equation, differentiate it with terms of gamma angle and equate it to 0. Okay, maximize or minimize conditions. So in this case, maximization of torque with respect to gamma angle. So if we do that, use this condition, we will be able to calculate out a ID current, okay, from this condition, and that is actually your reference current for the MTPA condition. Okay, and if we plot for various ID and IQ value of under MTPA condition, we get a trajectory like this. Okay, so for various value of and if I plot this torque, we get actually some hyperbolas here. The torque is a hyperbola if we plot them in IDIQ plane. So this is your rated torque, let's say hyperbola, rated torque hyperbola. So if we are operating with the rated torque, rated speed, then this is my operating point under MTPA for a IPMSM. So I have a particular IQ current. This is the IQ current, right, in the Q axis, and here is your ID, a particular ID current. So we need to find what is this ID current and what is this IQ current as my reference for MTPA. Okay. If I am operating with a lower torque, then let's say this is the operating point for a half the rated torque, let's say half the rated torque. Okay, so in that case again I will have a different ID and a different IQ, right? So for different torque conditions I can find these operating points, which is this trajectory actually. Okay, for various torque we can get various operating point, and they together gives us this MTPA trajectory. And this is your rated operation. We cannot operate somewhere here. If we operate here, we are outside of the current limit, so we cannot operate there. We are outside of current limit, outside of the voltage limit, right? And so up to the 0 speed to the rated speed, we operate along this trajectory up to here. Okay, and we can calculate out the ID and IQ. So next one is if we want to go to the flux weakening, what we will need to do, right? So concept of flux weakening we may understand from here. In your voltage equations, basically when speed increases, the major term that increases is your back EMF, EF. It will keep increasing, right? So if we do not do anything, at some point we will exceed our voltage limit, right? If we do not do anything to our voltage equation, then we will exceed our voltage limit. So in flux weakening, if we start to increase the ID current above what was in the MTPA, we will start applying a negative flux. Remember, your lambda D is lambda PM plus LD ID, but ID is a negative current, right? So as the ID current, negative ID current increases, lambda D flux will start to reduce. Okay, so that reduction is actually flux weakening. And when lambda D reduces, the voltage in a phasor diagram, if we want to see, so this is under the, let's say, twice the speed of the rated speed, twice the base speed. So your back EMF has increased, okay, but you have also increased your ID current, okay. So this term has increased. And increase of this term, what does also mean is that this reactive drop increase, right, which is in the opposite direction of your EMF. So resultant voltage is EMF and the two reactive drop together, right? So your terminal voltage will reduce. Okay, if we do not do that, if we would have kept the ID same as here, this voltage would have been much larger. It would not have been coming to the limit. Okay, so that means if it's a flux weakening, we need to increase the negative current, and increase of negative current also means that we are increasing this current angle gamma. So gamma angle is no longer at MTPA gamma angle. Okay, it will start to increase, and so we will need to calculate out what ID current we need for flux weakening. And this is again can be done from the equation, voltage equation here from this, and can be calculated out this ID equations. Okay, so if the characteristic current is outside of my current limit, so I am operating with MTPA up to flux weakening, so up to here, and then when I have gone above base speed, I operate in flux weakening. So my operating point, this operating point will start to move towards along the current limit circle, and whatever the voltage is, if let's say this is my voltage, twice the base speed as we have seen in the previous example. So if it's twice the base speed, this will become my operating point. Previously at rated speed it was working here, and then it moves, and let's say this ellipse relates to twice the base speed. So the cross section between the current limit and voltage limit related to this speed becomes my operating point. Okay, and how did I move from here to here? Through the flux weakening, by increasing the ID current. We have ID current here at MTPA, and here we have another ID current, and this ID current is bigger than the first ID current, right? So by increasing that ID current, I have moved to the second operating point, and so on. I can keep moving to various operating point relating to the voltage limit. So this ID current, negative ID current, can be calculated from that voltage limit equations. Okay. So if its characteristic current is outside, my last point of operation will be here. Okay, this is how I will be operating, and this will be my last speed. I cannot go any further. But if the characteristic is at the cross section of the current limit, okay, here, that means characteristic current and your rated current are equal, then theoretically you can actually keep going up to infinite speed through the flux weakening. Okay, so that's why, remember, we talk about we want to make characteristic current same as the rated current. So if we do that in the voltage limit and current limit circle, we can understand that we can keep getting flux weakening for infinite number of speed. Theoretically, okay, of course in reality you cannot go to infinite speed, because at some point the torque will become so low that you cannot even rotate anymore your rotor. So that will be your last speed point. And if the center of the ellipse is inside the current limit circle, then also you can get more flux weakening, of course not infinite, but you can get higher flux weakening range or constant power speed range than not than the center outside of the current limit. And when we have a condition like this, we can in fact get another trajectory called maximum torque per voltage. So this is somewhat similar to your MTPA trajectory, but this trajectory is limited by voltage. Okay, so the motor with very deep flux weakening, IPMSM, so they operate first in MTPA up to base speed, then they operate with flux weakening here, and after that, once they see the MTPP trajectory, they will operate along the MTPP trajectory. Okay, and for MTPP again, there is another way of calculating negative ID current. So it's all becomes how to calculate that negative ID current. Okay, in IPMSM for all these controls. You can see here some of our example done through using some of our IPM motors that has MTPP. You can see how the trajectory is followed, okay, during experiment. If you calculate the ID current correctly, that green point or green graphs is showing a real-time trajectory following for a prototype motor. And you can also see how the ID current is changing. So in MTPA, ID current was here. In flux weakening, ID current was dropping. And then MTPP, during flux weakening in MTPP, the current was lower. ID current was lower and dropping. And then once we got the steady state, it has come back to a lower value because we are applying low torque here. If we have kept the torque high, then the ID current would have settled here, okay? But we, in this case, I think we have applied low torque, so the ID current has come back here. And so you can see also IQ current, how the IQ current was highest under MTPA, but under flux weakening and MTPP it was dropping, okay? Now the main challenge for FOC is of course that current generation, the reference current generation using MTPA or flux weakening type algorithm, but that's a mathematical challenge. You can do it, okay? But the other challenge is you must have the information of theta because we need to do this transformation, right? DQ2 or DQ inverse. So if the encoder fails, your controller fails. So encoder is like your weakest link here. And there are some applications you may not even have a space to install the encoder. So here you are seeing where the encoder is. Okay. So if your load is very close to your motor, you may not even have space to install encoder. Okay. So there are situations where there is no encoder or there is possibility of encoder failure, especially in safety critical applications. If encoder fails, your controller fails, and it could be very, very risky. So for those type of applications, we need to have some kind of alternative, right? And that alternative is usually to have a position estimation as well along with the encoder. So for EV, they usually have also a position estimator along with the encoder, so that in case encoder fails, at least that position estimator can provide some like a buffer, okay? And position estimation can be done through many different methods. For sensorless control, if we do the position estimation, the correct position estimation is the most important part, okay? There could be sliding mode based observer based position sensor position estimator. There could be back EMF based position estimator and many more, okay? Other option is we use a complete different technique, that is the direct torque control. I don't know whether we have a break today. Yes? What time are we having the break? 10:30? 11:50, so we don't have a break at all. Okay, then fine. We'll move on then. Usually we take a break at this point. Okay, so let's then look at the second control technique, that is the direct torque control. Okay, and yesterday I mentioned that for direct torque control, it's inherently sensorless because it operates with stationary reference frame. So it does not actually need a theta. Okay, so how do we, what do you do then? How do you operate, and what is the basic principle? I guess again yesterday you have gone through a bit, right? The fundamentals of direct torque control. So for IPMSM, we do a transformation, but this is stationary framed transformation. Okay, I alpha, I beta. So to get I alpha, I beta, we don't need theta, right? The matrix is actually numbers, because theta is 0, so that matrix is all the numbers, so we can simply calculate out I alpha and I beta. And we may also need the information about voltage here, okay, because we want to calculate the flux linkages for DTC. Okay, so sometimes they use a DC bus voltage sensor. Okay, so you will have some current sensor to get your current information, and you may have a DC bus sensor for DTC, and using that DC bus information you can calculate out what is your V alpha and V beta. Okay, so once we have V alpha and V beta, we can calculate flux linkage. Okay, because flux linkage is integration of time integration of voltage only, right? But this voltage also have a resistive drop, so you first subtract that resistive drop. V alpha minus I alpha times R, and then you integrate it, you get your alpha flux linkage, and repeat that for beta flux linkage. So we will have alpha and beta flux linkage. We can use that flux linkage to estimate torque. Okay, because torque, as we have found, is 3/2 P lambda d id plus lambda q iq. It is also lambda alpha I alpha minus lambda beta I beta. Okay, so we know current, we know flux linkage in alpha and beta, calculate out the torque as our, or estimate our torque. Okay, we can also estimate the flux, because lambda, the resultant flux is the square sum of your lambda alpha and beta, right? So once we know lambda alpha, lambda beta, we can find flux linkage, we can estimate torque. And this becomes your feedback signal for the torque controller and a flux linkage controller. Okay, torque and flux linkage controller could be hysteresis controller here. You don't have to use PI controller. And output of these two is the error, torque error and flux linkage error. Okay, which then goes to a switching table. Okay, this switching table could be a lookup table. Okay, and output of this lookup table is the space vectors information, or the switches, which switch need to be turned on for how long. Okay, and that, and accordingly your inverter turns on and off. So we don't use PWM, we don't use SVM. We use this simply the output of a switching table to switch on certain switches at certain time. Okay, so you can see here how a this switching table will be developed. It based on that space vectors that we talk about. There were 8 space vectors. 2 of them are zero vectors and 6 active vectors. So application of active vectors for certain amount of time changes your flux linkage and your torque. Okay, that's the basic concept of DTC. So what we do is, let's say my torque error from the hysteresis controller is positive. That means I need higher torque. Okay, my motor is demanding higher torque as well as it demanding to increase flux. Okay, so in that case, and my reference voltage vector, space voltage vectors, let's say was in sector 1. So if I want to now increase this voltage, I apply voltage V2 in the anti-clockwise direction so that the resultant voltage is increased. Okay, so if the resultant voltage increases, flux linkage also increases, torque also increases. Okay, if my torque is same as what the reference is, that means 0, error is 0, torque error is 0, then I don't want to increase the voltage or decrease the voltage, right? In that case, I will apply a 0 voltage, V7. Okay, V7 is somewhere here. So it will keep the voltage, space voltage vector fixed at where it was. Okay. If I need to reduce torque, then I apply voltage vector 6, which is opposite to V2. If you can see here, this is your V6. Okay, this is your V6, which is opposite of your V2. Okay, because you want to now reduce torque, so you will be applying the vector that is opposite of V2, which is V6. Okay, and so on. So for various conditions, you can find out what voltage vectors need to be, and accordingly, you have to turn on and turn off these switches. So for example, let's say you want a V2, right? As in our previous case. So V2 means switch S1, S3 and S2 must be on. Okay, so that's the table, switching table. If I want V6, switch S1, S6 and S5 must be on. Okay, and if I want 0 voltage, that means V7, these 3 must be on. Okay, so this table, and such a table, lookup table, will be required for which vectors to be applied to the motor, and that decides which switch to be turned on. Okay, and which sector as well, because your reference, if your reference is here, let's say in this sector number 4 here, it will be completely different. Okay, so you have to also consider where your reference is, whether is it in sector 1 or 2 or 3 or where. So detection of sector is also another important thing for DTC. Using DTC, we can also do MTPA trajectory, but then MTPA trajectory becomes in the plane of torque versus flux linkage. Okay, we can also have a current limit circle. So you can see here the current limit is here. This weird shape graph is actually your current limit, which was the circle in FOC. Okay, but it becomes this polygon in torque and flux plane of DTC. And here is your MTPA trajectory. The voltage limits becomes a straight line. Okay, in case of torque versus flux linkage plane of DTC. So trajectory following can also be done in DTC. Flux weakening can also be done in DTC. Okay, but it's slightly different method. Okay, different way of calculating it. So again, you can see some experimental results here, how the MTPA is being followed and what's happening to your flux. Okay, you can estimated flux, you can see here. You can also plot that flux alpha, flux beta, which will become a circle and gives you the and shows you how it is varying, okay, when the speed is increasing. For this particular case, speed was increasing from 0 to 1500 or 1600 RPM. Okay. Yeah. So this is because you can see here the voltage factors are varying in a kind of a band, hysteresis band, right? And we are using hysteresis controllers, right? So because of that, you do not get like a smooth circle. Okay, it varies because it is instantaneous values, right? So it varies. You can't see a smooth circle. Theoretically, we should see that, but it's not the case. Okay, and this is the reason why the DTC is problematic, because you see a lot of this. There is high frequency harmonics as well. Okay, so that means your flux linkage has ripple. Okay, so that translates to ripple in your torque. So you get high torque ripple and high ripple in your flux linkage, causing your motor to not run smoothly under DTC with switching table. Okay, so as a solution, yeah, you can see here the comparison of FOC and DTC for a same type of or same applications. Okay, dark one is the DTC, sorry, FOC in here. This line is FOC, how smooth the torque is, you can see. Whereas in DTC, you can see a lot of ripple. The faint line is the DTC torque. Okay, so that means you will have high ripple in your torque, and you can hear that in your motor. It will start making noise. Okay, so how do you so that's one problem, the torque ripple. The other problem is, if you remember, in the flux linkage estimation, we need this drop I times R. So this R resistance value may not remain constant. It can change with temperature, right, as we know. So estimation of resistance may be required, accurate estimation of resistance. If we do not do that, we will be actually not getting correct flux linkages. Okay, and there could also be another problem with the inverter nonlinearity, because we use the to estimate V alpha and V beta, we use VDC, DC bus voltage, and the controller's output voltage, reference voltage. Okay, not the real voltage, actually, not the motor terminal voltage, because motor terminal voltage is PWM modulated, right? So if we want to use the real voltage, we have to use some kind of filter, and then designing that filter is not always easy, and it sometimes leads to actually wrong voltage. Okay, so preferred one is just use the reference voltage. So when you use reference voltage, you are ignoring the dead time effect of your inverter, which is the inverter nonlinearity. Okay, so that also means that flux linkage estimation may not be accurate, as accurate. So that leads to again the torque ripple problem. Okay, so these are the some of the problems, major problems or key problems, which has been then resolved, okay, by changing the switching table to a SVM technique and changing the hysteresis controllers to PI controllers. Okay, so instead of using hysteresis relay, then nowadays they use PI controllers, and that's why they don't call it anymore DTC. Instead they call it DTFC, direct torque and flux control, but through the PI controllers. Okay, so you eliminate switching, although we are still estimating the flux same way as before. Okay, or everything, the theory is still the DTC theory. Okay, still the DTC theory, but we are doing a transformation now. Okay, to apply SVM we need the reference voltages, right? And then only we can SVM or SPWM, we will need the reference voltage. So how do we calculate the reference voltages? Is actually use a transformation, and to use transformation you need an angle. So this angle is the angle between your alpha beta plane and an arbitrary plane called XY, because we don't know actually flux linkage is where. Okay, so it's an arbitrary XY plane, and so this angle, that's why it may not be your theta, it may be something either bigger or smaller than theta. It's an estimated theta. Okay, so this estimated theta may give us a separate or different reference frame, which is arbitrary reference frame XY. Okay, so that's the concept applied, and with this and to improve it further, because we still have problem with estimation of theta and the flux linkage and torque in this method. So to improve this problem, you can apply more advanced estimators such as observers. For example, in the next slide you can see that an adaptive sliding mode observer was used to estimate the flux and torque to make it more accurate. Okay, and so there are a lot of different methods how to reduce the torque ripple and the flux linkage ripple. So these two are one of the two solutions. Okay, there could be many more different solutions, so feel free to look at the literature. Okay, so that's your DTC, direct torque control advancement so far. We could run a completely full 5-day GIAN program just on control. Okay, so we only have 1.5 days. That's why we are giving you just the taste of it. Okay, rest you need to find out what's happening in the more recent times. Okay, I'm just only talking about just the basics here, right? Just the fundamentals. Then the most recent one that is being proposed comes from the DTC, actually, the model predictive control. Okay, and deadbeat control. In fact, deadbeat and model predictive control are now combined together. Okay, so again I understand you have learned a little bit about the fundamentals of model predictive, right? Yesterday? Yeah, so you learned what MPC is. So we will be looking at how it was implemented for a PMSM. Okay. For MPC, usually you need an encoder. Okay. MPC and deadbeat control is not sensorless, although you can make it sensorless if you estimate the theta, but it is not inherently sensorless as the DTC. Okay, because it works in DQ frame, so you need theta. Usually in the MPC, so you will be predicting the current of one sample ahead. Okay, and use a kind of a cost function to minimize the error between the reference current and the feedback current, which becomes your optimum space vector, which you will try to find through the cost function, which is your optimum space vector that will reduce the error between the reference current and the estimated current or the predicted current. Okay, that's the basic. And again, in the model predictive control, you can see we don't have a SVM or PWM. Okay, you get the switching signal directly. So you try to find what is the space vector, optimum space vector that will reduce the error between my reference ID current or reference IQ current and the estimated ID and IQ current or predicted ID and IQ current. And that to get this space vector, which switch I need to turn on. So it is kind of like your switching function. Okay, so you can see there is a it's actually came from DTC. Like DTC also, you try to find what's the space vector, right? If your torque increase, which space vector you need to apply. Here it's the same concept. You want to find which space vector to be applied to reduce the error between predicted current and the reference current. Okay, and so if we look at its implementation, so we start with our DQ equation, but we can write it as a state space equation, those dynamic DQ equations. Okay, we can write it as a state space equations, and we can discretize those equations, especially those the differential terms. We can discretize them. Okay, because it is the MPC is you can only operate with a discrete condition. Okay, it's not a continuous, it doesn't deal with continuous signal, it only deals with discrete signal. Okay, you must have digital signal processing there. Okay, so it's very basic is on discretization. So a differential current di dt can be written as the difference between two sample current at two samples. Okay, if we k is at one instant and k plus 1 is the next instant of the current. So difference between these two current divided by the sampling time is approximately equal to di dt. So that's the discretization concept here. And using that, you rewrite this state space equation, okay, as terms of some system matrix. So this system matrix, as you can see, they are function of your resistance, inductance, and sampling time. Okay, Ts is your sampling time, and of course the speed or electrical speed at that instant. Okay, at a certain instant. So this matrix A, B, and C all can be calculated or will be known. Okay, so if we know this matrix, we are these currents are at certain instant IDIQ. How do you get these voltages? We also need this voltage UD and UQ at certain instant. Okay, here where the deadbeat controller can come, or deadbeat concept can come. So using deadbeat, this UD and UQ can also be calculated. For example, I think, let me go back and see here whether I have a equation. So here, so this UD UQ can be calculated from the model, dynamic model of the motor again. Okay, and this is your familiar equation only, but in the discretized form, and use this equation or these voltages back in your predictive control, estimation of current control. Okay, So when we, and the cost function that we talked about in the previous slide, the cost function could be the very basic one is simply the difference between the predicted currents, okay, difference between the two predicted current of the one instant, okay. But we could add additional functions here if we want. So for example, in this second cost function, you are seeing that we have an additional cost function. This could be very commonly used as a switching frequent minimization, okay. When we use predictive control, since you are selecting the space vector that is optimum, so your space vector could be anywhere in the space plane, right? So if it is not adjacent to each other, then you may have to turn on and off your switches more, okay? So turning on and off the switches more means more switching loss, right? So that's why often in model predictive control, they also try to add an additional cost function of switching minimization of switching, okay? So this is an example of that. The issue here is, so you can see in the, when we have cost function, two separate cost functions as a summation, we have to provide some kind of weighing to the two of them, okay? This is for the current part, and this is for, let's say, your switching part, okay? So there is a weighing factor. Which one we want to prioritize, okay? Do we want to prioritize current prediction, or do we want to prioritize the switching? So how do we decide this weighing factor? So that's quite difficult, okay? And that's the main issue for MPC of this type of controls, like how to decide this weighing factor. So there are several methods being proposed to decide the weighing factor, but like it is still kind of research, okay? So this is something, if you want to work on, is active area to look into, okay? So next one, another problem with this, as we have talked about, so if we could do cost function, but when we use cost function, you are applying space vectors, kind of discretized space vectors, right? Similar to DTC. So you could have high torque ripple. You could have same problem as DTC, high torque ripple, okay? That's why sometimes what they do is, okay, similar to DTFC, they could use SVPWM. Instead of applying the vectors directly, find the reference voltages, apply SVPWM technique, and apply the pulses instead of the vectors, okay? So in that case, you will need some kind of controllers here, okay? Not just the cost function. You will need some kind of controller. The other one is, as we have mentioned, so you may combine the deadbeat control or deadbeat approximation of voltage, okay? So you calculate the voltages from a parametric model of the motor directly, and then use those voltages to predict your current in your equations. And then you may use SVPWM or cost function, okay? Yes. That's the issue, right? That's what I am about to say. So in this type of controls, we very much relies on this parameter, resistance, lambda PM, LD, and LQ, right? And we assume they are same, they will remain same whatever we have measured offline, right? But we know resistance going to change with temperature. Lambda PM can also change with temperature. As the magnet changes with temperature, we know, right? And LD, LQ can also change if you go to nonlinearity, okay, if we have saturation. So parameter, there is a uncertainty of the parameter when we use this type of controls, including FOC. Okay, and that may, because of that, there could be deterioration in your controls. So parameter estimation is a one of the important research area as well. Okay, so you try to estimate the parameters online if we can. You can use the if you use offline estimation, you try to find how the LD and LQ, let's say, is varying with current. Okay, so LQ usually, because there is saturation, LQ always usually reduces as the saturation increases. So LQ is not actually a constant. So in your model, you can instead of using LQ constant, you can find a function of LQ as a function of current, okay, from these measurements, and then use that in your control estimation, while you are estimating those flux linkage, etc. Right? So that's the easiest way to do. But this still does not actually eliminate the uncertainty, because these measurements are done offline under usually some special conditions. So we cannot guarantee that the inductance is varying same way as we have measured offline. So that's why they try to do it online. So there are various methods as well to estimate all the 4 parameters online. Okay, and that's again a very active research area, how to estimate those 4 parameters accurately online while using them to estimate the flux, torque, etc. in your control. Okay, even in FOC you may need to estimate the parameters more accurately online. There is also like the more advanced one, what they're talking about is model-free predictive control. Okay, so you do not use those parameters at all. Instead, you try to find that some disturbance caused by the difference between the real model and your theoretical model, okay, and a real model in the machine. So that can be estimated as a disturbance signal, okay, and then use those disturbance signal in disturbance observer to control the motor, which is the idea behind the model-free predictive control. Okay, and this is only just coming. Okay, model-free predictive control is only just coming. So there's probably, means it's not fully established yet. It's only beginning. Okay, and it could be a very interesting area to look into as well, since it should eliminate that parameter uncertainty. Okay. Yeah, I think we could stop here if we want and open it for the questions and discussions. Yes. Okay, so position estimation. Let's go to the position estimator as maybe, sorry? Yeah, so that, like, no, I'm just trying to find a position estimator. If I have a figure, it will be easy to explain there. All right, let's take this, even if we can take here. Let's go back to DTC maybe. Let's look at here, okay? So we are finding that position theta here, this theta, right? It is the same way we will estimate also if it is a position sensorless control. So to estimate theta, what we are doing is this finding or integrating a voltage, right? So this V alpha, let's say V alpha is it's actually the current I alpha R plus the back EMF alpha component, right? So this component E alpha is in fact, as we have talked about, omega times flux linkage alpha, right? So if your speed is low, this component is very, very low, right? Very small. And it could become close to I alpha R. So you are getting, that means your flux linkage nearly zero. So your theta estimation is, because you are dealing with a very, very small signal, your noise and your real signal becomes you cannot separate them, right? So estimation becomes very difficult at low speed. Okay, that's the issue for sensorless control at low speed when it depends on this back EMF. Okay, and as a solution, they said you can use the high frequency injection, and as we know that inductance is position dependent, that inductance will form. So at high frequency we can separate out the inductive component, the position dependent inductive component, and from there we estimate theta. And theoretically it's possible to estimate theta even at zero speed if we use high frequency injection. Okay, so that's the thing. Any other questions? Yeah. You can do stationary frame, I think, but then the main issue, I think, with a stationary frame is it's a similar issue as the DTC, okay? Because if you do it like DTC, what we do here, right? So here we have flux linkage, but in model predictive you have to predict the current. Okay, so you have to predict I alpha, I beta prediction, okay, based on the model, right? So if we go back to MPC, so this will be then your alpha beta transformation, and these will be alpha current and beta current. Okay, I don't know. Do you know, Vinay? Yeah. If we have weighing factors. If we have weighing factors. So like if we only use this one, that here you have only one cost function, right? It's only the current. Then you can use I alpha, I beta as well, okay? But if you want to also include switching loss minimization, then finding this weighing factor is very difficult. That's what he is saying, okay? With alpha beta frame, finding this weighing factor even more difficult, more challenging. And this is actually important to have switching loss minimization, because you know when we are using prediction, your space vectors could be anywhere in that space, in that hexagonal plan, right? So if it is anywhere, you may be turning on and off some switches unnecessarily. Okay, so switching loss is always higher in this type of control, cost function based control, and that's why this switching switching loss minimization becomes part of your cost function. And then if it is cost function based, it is part of it, then that weighing factor determination in stationary reference frame is challenging. Okay, so that's what it's. You can do it. There is no problem implementing it in alpha beta, but you may not get the optimum performance of your whole system. That's the thing. Okay, so my last comment is actually so for model predictive control, you can see there are many different types. There is this, I will probably provide you with this reference. It's a very nice reference coming out recently. So predictive control can be classified into these three different categories. Okay, one is that we talk about the deadbeat predictive type. The other one is finite set model predictive control, under which we have multi-vector application. So remember, we talk about we apply only one optimum space vector. So if you apply only one space vector, that leads to those flux linkage ripple problem, torque ripple problem. So people are proposing to use more than one space vector, selecting more than one space vector, which is called multi-vector selection model predictive control. So if you do that, it seems to improve it, that ripple. So your idea of stationary reference frame, you may try to see whether by multi-vector selection you can use or eliminate that switching function weighing problem. Okay, they have got up to three vector. So instead of selecting one, you select 2 or 3 vectors. Okay, 2 or 3 space vectors to find your optimum space vector. Okay, and then the other one is the it's called continuous set model predictive control. The main issue, I think, with continuous set is that you may need much more new computational resource. Okay, because you are predicting it continuously, not in discretely. Okay, so that's the issue with the continuous set one. You may need a much powerful microprocessor to do this type of model predictive control. Okay, so they have also, and this is also a good comparison, the method which requires PWM or as PWM and or which does not. Okay, and some of the other controls you may not, because remember you are selecting your reference space vector, so you may not be able to fix your switching frequency. Your switching frequency of the inverter could be variable. Okay, again there is some method how to fix the switching frequency and switching rate also for DTC actually. Okay, this is the same problem for model predictive DTC, the variable switching frequency. Okay, or variable switching rates, and that relates to your switching losses basically. Okay, so this comparison, and this is a reference paper recently come out. I think it's a pretty good reference. I might have that as a reference in my reference list, and I will provide that with the slides. Okay. The last one I wanted to say is that this course is not the end. Okay, just the beginning for you. Okay, just only show you what is possible, what can be done. Okay, and it's open to you to take it from here. Okay, that's what I wanted to say. All right. Yep. All right. Thank you. So we'll have a break. Okay. All good. So we'll have a break, and then we'll have the validation, and then we'll have the exam, and then the lunch. Okay. Thank you. Enjoy the break.